Hello, I'm an old guy and I do maths. Today we're going to have a look at binomial theorem, which when you see it written out algebraically looks terrifying. So we're not going to deal with that element of it until we get to the end of this video. What is binomial theorem? It's a method by which you take a binomial expression raised to a significantly ugly power and you expand it. And there's a pattern to this, as is so common in mathematics. What we're going to start out with, though, is some recognizable expansions. We're going to start off with a perfect square. A plus b all squared expands to a squared plus 2ab plus b squared. I'll explain the red ink in a minute. A plus b cubed is the linear factor a plus b times this, the perfect square. And as a result, we get a cubed plus 3a squared b plus 3ab squared plus b cubed. If we raise it another power, a plus b to the 4, we take the two perfect squares that we got here, and we multiply them by each other. What we wind up with is a to the power of 4, 4a cubed b, 6a squared b squared, 4ab cubed plus b to the power of 4. Now, the question is, how do we get the coefficients? Anyway, that's the first question I'm going to answer, because it's the most straightforward one. There are a number of ways of doing this. Calculator is obviously easiest, but for those of you who like a challenge or who are not allowed to use a calculator, this is how you go about it. This will be immediately familiar to those who have done a little bit of probability or have seen Pascal's triangle before. If you haven't seen Pascal's triangle before, I have a video, short video explaining how it's created and some of its uses. You're about to see one of its uses, and I will explain again quickly how it's created. So with Pascal's triangle, you start off with these three ones. You add 1 and 1, you get 2. 1 there, 1 there. You just place ones along the outside of this triangle. 1 and 1 is 2, so you get a pattern 1, 2, 1. 1 and 2 is 3. 2 and 1 is 3. Place the ones there. 3 and 1, 4. 3 and 3, 6. 3 and 1, 4. And so forth and so on. And what you will have immediately noticed, I hope, is that at this point here in Pascal's triangle, we have the coefficients of each of the expressions in this binomial expansion. And if you look up the page a little more, you'll see that it is indeed a pattern that works. So this is the set of coefficients for an expansion to the 4th power, this for the 3rd power. Now, one little quirk is that it's on the 5th line and the 4th line respectively. So this is, we'll do this in red ink, this is a plus b to the power of 1, 2, 3, 4. You don't start there, or if you do start there, you add 1. And this is a plus b to the 3rd. Okay, so that is the easy way of sorting out what these coefficients will be. Right. There is a harder way, or a more laborious way, let's put it that way. Okay, so again, those of you who've done a bit of probability will recognize this. This is a combination, and what it says in plain English is n choose r. N being the range of a set that you might choose from, and r being the number that you want to choose from that set, and it sets out the possible combinations. Okay, so how does this apply to binomial theorem? Well, it allows you to generate these coefficients, but it is a bit more laborious. And this is the formula for n choose r. So n factorial, factorial is simply, let's say we take 4 factorial, that is 4 times 2 times 3 times 1, over r factorial times n minus r factorial. Well, that's all very helpful. What does all this mean? Okay, well, let's see what it does mean. So another way of writing this is you'll sometimes see it set out in tall brackets like this, and you might see n r like that. That is an r, badly written. N choose r, 3 choose 1. Okay, so what we're going to do is we're going to work out this coefficient using this model, and you'll see why Pascal's triangle looks such a breeze by comparison. Okay, so we're raising this expression to the power of 3. So this is the expansion of a plus b to the power of 3. That is n. So that number goes there. Okay, and the 1 is probably most easily explained as being the power of this expression here, this pronumeral here. So if we were along here, n would still be 3, but r would be 2, and so forth and so on. This is slightly confusing, I admit, and it's why it's not my preferred method. It's also laborious. Anyway, we're going to work out how we get this number. So 3 factorial, n factorial, over 1 factorial times 3 minus 1 factorial gives us 3 times 2 times 1, 1 factorial, 3 minus 1, 2 factorial. We do a little bit of cancelling and we wind up with 3. You can see why that is more convenient, can't you? Okay, right. So that's our little diversion into factorials. I don't really recommend it as a method. And of course, there's always the calculator. I think most graphics calculators have a function for this, and permutations as well, but that's another story. Okay, so where are we at? Well, we had established what our coefficients would be, and we had done that primarily using Pascal's triangle and getting these coefficients of our expressions, which you see here. So I've rewritten this, and now we're going to have a look at how we get the various pronumerals raised to their correct power. Now, we are dealing with a plus b to the power of 4. That's important. So what can I say? Mathematics is about patterns. Notice that we start off with a to the power of 4. The next expression has a to the power of 3, 2, 1. And if we could be bothered putting it in here, it would be a to the power of 0, which is simply 1. So there is a pattern. We start off with the first pronumeral here raised to this power, and as we move across the equation, or the expansion, this drops by 1 with each expression. At the same time, b, having started off as b to the 0, because remember a winds up as a to the 0, increases by 1. 2, 3, 4. So how do we reduce this to some sort of formula that's comprehensible? Well, we'll come to that, but let's just talk about the method that was used to get to this point. Pascal's triangle, first step, gave us the coefficients of each of these expressions. Then we took this pronumeral, raised it to that power, and moved across the expansion, reducing the power by 1 at each step. We took this power and started with 0, raised it 1, raised it 1, raised it 1, and eventually it wound up as b to the 4. So what you would notice is, of course, that this started off as a to the 4. So as this decreases, this increases in terms of its powers. Now, the next thing that you're going to see is you're going to see an algebraic rendering of all of this, and I'll do my best to explain it, but it's probably a bit more confusing than what you've seen. Okay, we're in the last lap of this this exercise, and here's a slimmed down version of the algebraic expression of binomial theorem. So we have a binomial expression, a plus b, and we raise that to the power of n. So our coefficient for the first expression will be n choose 0. Now, you can go through the process that I outlined using combinations to get these numbers. It's much easier to use Pascal's triangle. Anyway, the next thing is to note that a is raised to the power of n and b is raised to the power of 0. So this number here, this number here. Next expression, n choose 1. A is raised to the power of that minus 1. We've already seen this pattern, so if this were, say, to the power of 5, this would be 5, this would be 4, this would be 3. B to the power of 1. Next part of this, n choose 2. So a is raised to the power of n minus 2, whatever number n is, and b is raised to the power of 2, and so forth and so on. That's it. Thanks for watching. We made it through, and I hope that this was clear and intelligible. See you next time. Bye.